Welcome to The Explainer. Today, we are jumping into something pretty cool, predicting the future. We're going to be diving into time series forecasting, which is really just a powerful way of seeing what might be coming next by learning from what's already happened. Okay, so at first glance, predicting the price of a house and predicting the price of a stock, they seem kind of like the same thing, right? But they are worlds apart. Think about it. For a house, you can list its features, square footage, bedrooms, location, in any order you want. It doesn't change the house. But for a stock, the order is everything. Yesterday's price has a direct impact on today's, and that will affect tomorrow's. That simple arrow of time, well, it changes the entire game. So here's our game plan. First, we're going to dig into why time is so unique. Then, we'll become data detectives and learn to spot hidden patterns. After that, we'll break the data down, make some surprisingly simple predictions, and finally, we'll grade our own work to see how we did. All right, let's kick things off with that one simple rule. You just can't shuffle time. And as we're about to see, this one little thing completely breaks the standard rules of prediction. You know, in most data science problems, every row of data is its own little independent event. You can shuffle them all up, then you don't lose anything. But with forecasting, the data is telling a story. Each point is a word in a sentence. If you shuffle the words, you just get nonsense. The sequence itself is the single most important piece of the puzzle. So now that we have a healthy respect for the order of time, we can start looking for the clues it leaves behind. It's time to learn how to spot the patterns that are hiding right there in the timeline. The first, and honestly, the most obvious pattern, is the trend. This is the big picture movement. Is the data over a long period generally heading up? Or is it sloping down? Or maybe just staying flat? It's the basic direction everything is going. And here's a perfect real-world example. This is sales data for anti-diabetic drugs in Australia. You don't need some fancy model to see the story here, do you? Over almost 20 years, there is this clear, steady, upward climb. That right there is a trend in action.
The second key pattern is seasonality. And these are the predictable rhythms that are tied to the calendar. You know, think about ice cream sales going way up every summer or retail sales spiking every December. It's a pattern that has a fixed, known, and repeating cycle.
Let's go back to that exact same drug sales chart. Yeah, the overall trend is going up, but look closer. See those sharp peaks and valleys that happen over and over every single year? It turns out a government subsidy policy actually encourages people to stock up before the end of the year. So that predictable drop every January, that's its seasonal signature. So our eyes can spot these patterns pretty well. But how do we prove they exist, with math? For that, we use a really cool tool called the autocorrelation function, or ACF. It's really just a fancy way of asking a simple question. How much does the value today depend on the value from yesterday, or last month, or exactly 1 year ago? And when we run this on some quarterly beer production data, bam, the pattern just jumps off the page. We see these huge spikes at lags 4 and 8. That's the mathematical proof right there. It's telling us that production in any given quarter is strongly tied to what happened a year ago and even 2 years ago. We've just mathematically confirmed a strong yearly pattern. Okay, so spotting patterns is step one. But to do this right, we need to neatly separate them. We have to take the data apart and look at each individual piece. I love this way of thinking about it. A time series is like a finished song. It's got a bass line, that's the trend. It has a repeating drum beat, that's the seasonality. And then it has some unique little mistakes and flourishes, that's just the random noise. Decomposition is basically the process of putting on the studio headphones and isolating each of those tracks. And the process itself is actually super logical. We start with the raw data. First, we use some tools to smooth it all out and pull out that long-term trend. Then, we find and extract the repeating seasonal cycle. And whatever is left over, the stuff that isn't trend and isn't seasonal, we just call that the remainder. And here is where the magic all comes together. Look at the top chart. That's the original, kind of complicated data for U.S. retail employment. But below it, we see it broken down into its 3 parts. A nice, smooth trend, a perfectly repeating seasonal pattern that spikes every holiday season, and then the random stuff that's left over. You can literally see how if you add those 3 bottom pieces back together, you perfectly recreate the original complex data. It's amazing. All right, now that we can see all the pieces of our data, let's actually start forecasting. And we're going to begin with some methods that are so simple, you might actually laugh. but trust me, you'd be wrong.
Now, here is the absolute crucial point. Before you build some super complex AI model, it must prove that it's better than these dead simple ideas. The mean method just says the future will be the historical average. The naive method says tomorrow will be exactly like today. And the seasonal naive method says this December will be just like last December. Any fancy model that can't beat these isn't worth your time.
And when you put this into action on our beer production data, you see the difference immediately. The mean and naive forecasts, they're just flat lines, completely missing the rhythm of the data. But look at the seasonal naive forecast. Wow, just by copying last year's pattern, it's doing a brilliant job of capturing those ups and downs. It's not perfect, but it's already playing the right song. So, we've made our forecasts. And now, the moment of truth. How do we actually know if they're any good? It's time to grade our own homework. Okay, so our eyes told us the seasonal naive model looked the best on that beer chart, right? But we can't just go on looks. We need to prove it with cold, hard numbers. So which one really won? This table shows a few different ways to measure how wrong our forecasts were. Let's just focus on one, MAE, mean absolute error. That's just the average amount our forecast was off by. For all of these numbers, lower is better. And just look at the row for the seasonal naive model. I mean, across every single measure, it's not even close. The numbers prove what our eyes suspected. It is the clear winner.
All right, so let's recap this whole journey. The biggest takeaway? With time series data, order is everything. We learned how to spot the key patterns, trend and seasonality, and how to take our data apart to isolate them. We saw that incredibly simple models are not just useful, they're essential benchmarks. And finally, the golden rule. Always test your forecast on data it has never seen before.
And that leaves us with one final, fascinating thought to chew on. The fact that a ridiculously simple model, one that just copies last year's value, is often so incredibly hard to beat, that tells us something really profound. It forces us to ask, are the systems driving our world really as complex as we think they are? Or are they governed by surprisingly simple repeating rhythms?